Alright, I'm going to work 1613 example, and I used to actually give a very similar problem on one of my tests, so I wouldn't count on it now, but I think it's a pretty cool problem. We have a rigid body horizontally, and it's 10 meters long from A to B. We are given that the velocity at A is equal to 2 meters per second, right here, and that the acceleration at A is 3 meters per second. We are given that it is 45 degrees down. Alright, and that means the motion over here is going to be at 45 degrees up if this is on a 45 degree incline. So that's some constraints that we're going to use, and they are asking determine the angular acceleration, so alpha, and the acceleration of B itself. The first thing that you should do, I'm going to skip just because we've done it many times, or I have in the past few videos. I'll do some geometry for you, or I'm going to do some drawing, I'll let you do the geometry. Is taking A and B, and we need to find omega if we're going to use the acceleration equation. This thing right here is a function of omega. We need to know what omega is about this rod as well, or in order to find alpha. So if we know this one goes down at 45, this one goes up 45, we can do a little thing like this. This would be your position vector 2b from the instantaneous center. This would be your position vector 2a from your instantaneous center, where this is the instantaneous center. Alright, now from that, and knowing this is 10 meters, doing some geometry, you can find out what omega is, and omega ends up being 0.283 radians per second, and it's going to be going this way, positive k direction. Okay, now we can use the acceleration equation, where the acceleration of B is equal to the acceleration of point A, back up, of point A, plus alpha crossed into R of B with respect to A, minus omega squared, that's the scalar, because all the components cross out except for the one that points back towards A from B. So this is still a vector. Alright, now what we need to do is put it in component form, or vector form. So I'm going to just do a coefficient A, B, and it's going to have a I component in the cosine 45 direction. It's going to have a J component in the sine of 45 direction. Alright, that's this part right here. Now I'm going to take care of the acceleration at A. I'm going to say the acceleration of A, and your book is going to tell you that the acceleration of A going down like this, they're going to just assign signs to it. But really, if we think about what angle that is, it is 335 degrees. And if we use that angle, we don't have to worry about putting our own minus signs in. So I'm going to write, and you can check out what I do versus what the book does. AB cosine 45, sorry, I just did what the book did. Cosine of 335 plus AB sine of 335. Alright, that's this first term. We also need to cross R into, or alpha into R. So I get, we can call it alpha, that's what we're looking for. We just need to assign it a direction, and that's going to be in the positive k. If we gave it a wrong assignment here, we would just get a negative later. We need to cross that in to the position vector of B with respect to A, and that's just 10 meters long in the I direction. Okay, we just need to do the plus omega squared and minus omega squared, where omega we have, so I'm going to go ahead and put that in, a minus 0.283. Just don't forget to square it, and it's going to be the same vector, 10 in the I direction. We just hold on to the minus sign from it. Alright, now carry out all the cross products, the one cross product, and then equate the I's, J's, and K's. What we'll get is an I. Let's use some color. We have an I component here. I better carry this out. AB cosine 45I plus AB sine 45J is equal to, I'm just copying down so far, A of A cosine 335 plus AB sine of 335. Alright, if I cross K into I, that's going to give me alpha times 10, and I, make my little chart, K into I is going to give me a positive J. Alright, then I have a negative 2.8, oh, I can't do that, 0.283 squared times 10, and that's in the I direction still. Alright, so I have an I, sorry, this has an I, this has a J, here's an I, and here's an I. So I get A, B, times the cosine of 45, we can drop the I now, is equal to AA cosine of 335 minus 0.283 squared times 10. Alright, we still have two unknowns here. So let's get the J components. So on the left hand side I'll get AB sine 45, drop J, is equal to AB sine of 335. And we almost forgot that one, plus alpha times 10. So this is for our I's, this is for our J's. Alright, and we know everything actually. This is an A, I'm sorry, I lost my notation. We know the acceleration of A that was given to us. We are searching for the acceleration of B and alpha. So two equations, two unknowns. We're done. Get alpha. Acceleration of B is 1.87 meters per second squared, and it's going to be going up at an angle of 45. We can tell that from the picture. It's not coming off the surface. And plugging back in, we get an alpha of 0.344 radians per second squared. You can do this with scalar analysis. I recommend practicing with vector analysis. Rigid bodies require a lot more vector analysis, so just get your practice in.